Hi everyone, this note is on Newton's law of cooling. So let's read what this says here. It says when a hot liquid is left out, it will cool according to Newton's law of cooling. And then this equation right here represents the law of cooling, where T is the final temperature of the liquid and M is the number of minutes, okay? The other variables where you've got B, A, and K will vary according to the type of liquid, the initial temperature, and the temperature of the surroundings. So let's take a look at our first example. It says the temperature of a cup of hot water can be modeled by this function. T of M equals 60 times 1.05 to the power of negative M plus 21. So just a quick note that the B value here would be 60. The K value here is 1.05, and then the A value is 21, okay? So the first thing it asks us to do is find the initial temperature of the water. Well, the initial temperature of the water will happen when M equals 0. So we're going to sub in M equals 0. So here I'm going to say T of 0 is going to equal 60 times 1.05 to the power of 0 plus 21. Well, what does this mean? I'll get T of 0 equals 60 times anything to the power of 0 is 1 plus 21. So that means T of 0 is going to be 60 plus 21, so it would be 81. So the initial temperature of the water is 81 degrees Celsius. Okay, now it asks us to find the temperature of the room. Well, let's take a look at what this is going to look like. So for starters, we know that T of M is going to equal, the equation is 60 times 1.05 to the power of negative M plus 21. But this negative M that we have right here means that I can, because the exponent is negative, I can rewrite this as 60 times 1 over 1.05 to the power of positive M plus 21. So now if I were to calculate this 1 over 1.05 that we have here, it's about 0.95. So this would be 60 times 0.95, but there's more digits to it, plus 21. Now we know that the initial temperature is going to be 81 degrees. And we also know that we have a horizontal asymptote here at 21, because normally we would have a horizontal asymptote at 0, but because this shifted up by 21, we have a horizontal asymptote now at 21. And because this right here is less than 1, we know that we have exponential decay. So it's going to look like this. So as you can tell right here, the temperature of the water started at 81 degrees and it's gradually decreasing until it levels off and it tries to reach the temperature of the room. And what temperature is it trying to reach? This 21 degrees right here. Okay, and that's how you do part B. Okay, now in example 2, it says a cup of coffee has an initial temperature of 180 degrees. So that's going to be some useful information here. And the room is 76 degrees. Given that the temperature of the coffee can be modeled by this equation right here, first thing we want to do is determine the values of A and B in the equation. Well, this A right here represents that asymptote, right? So it's going to look like this. And it's going to start at some initial temperature and it's going to reach this asymptote right here. What is the asymptote that this is going to reach? It's going to be the temperature of the room. So therefore A equals 76 degrees Fahrenheit. But now we need to find out what B is. So to find B, I'm going to sub in the 0.0180, because this right here is the initial temperature, and the initial temperature will happen at time 0. So here I'm going to say 180 equals B times K to the power of 0 plus, and now we know that A is 76, I'm going to say plus 76. And now I can go ahead and evaluate. So right here, this is going to be 180 equals b times anything to the power of 0 is going to be 1 plus 76. So b times 1 is just b. Subtract the 76 from the other side, and you end up getting 104. So therefore, b equals 104. And A is going to equal 76 degrees Fahrenheit. Okay? Okay, so then part B says, after 5 minutes, the temperature of the coffee is 168 degrees. Let's write this out as a coordinate. So after 5 minutes, the temperature of the coffee is 168. We also know that our equation now, this equation that we have here, we know the B value is 104. We don't know the K value, but we know that the A value is 76. So now I'm going to sub in the 0.5 168. So 168 is going to go in for T, and that's going to equal 104 times K to the power of negative M, where M is going to be 5, so negative 5 plus 76. Okay, so now what I have to do here is subtract the 76 over. When I do that, I'd end up getting 92. Then I'd want to divide by this 104. So it'd be 92 over 104 equals K to the power of negative 5. Now this gets a little bit tricky because I have a negative exponent. So what I'm going to do to make my life easier is I'm going to do the reciprocal of this value right here. Because in doing that, I can now say that this is a positive 5. Okay, so I could either do the reciprocal of the base and get rid of the negative, or I could just do the reciprocal of the constant on the left side right here. And now I can say that this is K to the power of positive 5. Okay, cool. Well, how do I get rid of this power of 5? I just have to take the fifth root. So this would be the fifth root of 104 over 92. And now I would type that into my calculator. So now I have two options. I could either write 104 over 92 to the power of 1/5, because the fifth root means I'm raising it to the power of 1/5. Or if your calculator has the button, we could do the fifth root of 104 over 92. And so this, we still get the same answer right here. So here we can say K equals approximately 1.02482353. Okay. All right. So then question C says, what would the temperature be after 10 minutes? So here I would use the equation T equals 104 times this 1.0248 blah, 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 to the power of negative 10 plus 76. But I don't want to use this value because this value right here is a rounded value. And I would rather use an exact value. So what I'm going to do is I'm actually going to store this in as K in my calculator. So here I'm going to say K equals, and in class, I'll show you how to store numbers into your calculator so that it makes things a little bit easier. And then now I can just type this all in. So this would be 104 times, and then I can just put in K because it knows what K is, and it knows K is equal to that value, to the power of negative 10, and then plus 76 right here. And I end up getting about 157 degrees. I just want to show you something. If I had used a rounded answer, so here, if I had used like 1.02, for example, raise that to the power of negative 10, and then add 76 to that, I would end up getting 161 degrees. So I would be off by 4 degrees here. So that's why it's really important that you use the exact value and not the rounded value. So you have to store this into your calculator. Or one last option that you have is you can actually type in 104 times, and then you can actually use this value right here, this fifth root of 104 over 92. So I could say the fifth root, of 104 over 92, and then raise that to the power of negative 10, and then add 76 to that. And it's exactly like what we did up here. Okay, so you've got a couple options. I'm happy to help you with your calculators in class to help you get these more exact answers. So this right here means the temperature would be approximately 157 degrees Fahrenheit. And that's it for this video. Let me know if you have any questions. Otherwise, I'll